Okay, so exercise 6 of list 4. List 4 here. So it's a very short statement. It's an exercise on the Poisson distribution, okay? I suppose that x follows the Poisson of parameter lambda, and I want to prove that the probability that x is even is strictly greater than the probability that x is odd. Okay? So it's what I have to do. Okay? So, first, you have to know the definition of what is a Poisson distribution. If you don't know, the exercise is finished here. Okay? So if I follow a Poisson distribution of parameter lambda, lambda being strictly positive, okay, I remind you. But the probability... Non, mais moi je mets tout en Ethernet. The probability that x... Okay, it's because it doesn't work in general if you use Wi-Fi, so that's why I use Ethernet. So tell this, so you are always late, always. Okay? So you will remind me your name at the end in order to write you as present. Okay? So the probability that x is equal to k is equal to exponential minus lambda, lambda to the power k over k factorial, okay? And this is true for k belonging to n. The only values I take are in capital N, okay? It's just the definition of a Poisson of parameter lambda, okay? So before to check if one is greater than the other, okay, but I have to have a look on the events and to see if it's possible. Are you okay? You seem to be surprised. Okay? This one. So it's the mask. Okay, with the mask it's complicated to. Okay. To be surprised, to be happy, to be sad. Okay, it's the same. Okay, so I am interested in x is even. So what is the meaning of this one? So it means that x can take the value 0, or the value 2, or the value 4, or the value 6, and so on. Okay, so it's like to be, okay, an even number. Okay? So if you want, I can write it this way. X equal to 0, disjunct union x equal to 2, and so on. Something I can write shortly as it's a disjunct union from k equal to 0 to plus infinity of what? X take the value, which parameter I can put to k. Okay? X is equal to 2k. So this is the event, x is even. And this is true for any kind, okay, of discrete random variables. In the same way, to be odd, it's the same thing, x equal to 1 or x equal to 3, and so on. Once again, it's something that is very general. For the moment, I use nothing. Okay? I use nothing for the moment. Only the fact that I know that x take values in capitals. I have sequences of pairwise division sets. Okay, so I am in the situation where I can use I have called the sigma additivity. That is, when I have a sequence of pairwise division sets, the probability of the union is equal to the sum of the probabilities. Okay? So, let's write it this way. And now we are going to start to use our hypothesis. Okay, because for the moment, the fact that X is a Poisson or not, okay, means nothing, so I just check that it works, and it seems to work. Okay. So now I replace, okay, I have the definition of to be a Poisson. Is this one, and I just plug inside. Okay, and after we are going to compare this quantity if possible. So it's the sum from k equal to 0 to plus infinity. So it's x equal to 2 times k. So I have just to replace k by 2k inside. Exponential minus lambda, lambda to the power 2k over 2k factorial. Okay. I take the definition of being a Poisson, and I want the probability that x is equal to 2k. I just replace k by 2k in my expression. And I do the same for the other one. Job, the statement of the exercise. So for the moment, I have just expressed in a better way what I have to prove, the quantity involved in what I have to prove. And now we are going to try to compare them. Okay? So do you have an idea? A natural idea, that is in general what we do first, okay, when we have this kind of thing to do. Yeah. Yeah. Because it can be written as 2 times k for k belonging to n. Okay? Because for you it's not the case. I know that it depends on, in fact, it's like a convention, let's say. For me, what I call even numbers are the ones that can be written to the form of 2 times an element in capital N. And something that is odd is something that can be written 2k plus 1, k belonging to n. Okay? In this exercise, it is important because, okay, for k equal, if you consider that 0 is not even, okay, it means that we'll have a term missing in the sum, and maybe it can change the inequality. Okay, so we have to be clear on this. Okay. It will be my convention in this course. I know that in some countries, sometimes, okay, 0 is nothing. Okay? But it's that clear that in fact 0 is even, okay? I don't want to enter into more considerations, but for me, odd and even are a partition of capital N. Okay? So do you have an idea to compare?
Can we divide the sums?
You can do anything you want. Okay? The problem is that, okay, if you divide 2 sums, you won't be able to simplify anything. Okay? So you can. But it will give you more or less nothing. You like to divide products because maybe you can simplify, but divide sums, okay? Not that interesting. Find the expectation. No, because it's really this quantity I am interested in. And here you have numbers, huh? So expectation of what? This one is an event, it's not a random variable here. Huh?
We can take the one.
The?
The one. We have plus one.
Sorry. You have to say?
We have plus one, so maybe we can take the lambda left, lambda out, and then the factorial will simplify without the one, and then we can just compare with the something.
So if I have understood what you say, it means that you want to compare what I have inside. Is what you say or no? Yeah? Yes, it's a first and good idea. In general, it's what we do. Unfortunately, it won't work in this situation, but it's what you have to do first. I want to prove that this one is greater than this one. If I am sure that all these terms are greater than all this one, it will be okay. So let's see what happens. We are going to see that it doesn't work, but it's natural idea. I will come back to you after. Okay? So I want to prove a strict inequality. A natural idea is to check if it is possible to compare this one and this one, because I'm agree that we will have a lot of simplification, in fact. So if I try to compare exponential minus lambda 2k over 2k factorial, here typically if you want, no, you're right. If you want to compare, I don't remind your name, but the one that want to divide the sums. So, divide two sums is not a good idea. But in this situation here, you have to compare maybe this number and this number. So instead of taking a difference, it's better to take the ratio here because you have a lot of products. So here, it's that natural to consider ratio instead of considering difference in order to see if someone is greater than the other. Okay? So if I take the ratio of the two general terms of my sums, if I am able to prove that this one is strictly greater than 1, my job will be okay. So let's simplify what happened, okay? So I can simplify a lot of things here because my general term, okay, is as the form of a product. So I can simplify this one and this one. I can simplify lambda to the power 2k and this one. And I can also simplify the factorial. At the end, I obtain 2k plus 1, okay, over lambda. Yes, there is. Are you okay? And what can you say? Well, it depends on k. And so I can conclude this way. Because this one will be strictly or less than 1. I don't know. But I am not able to conclude. It depends on the value on k and the value of lambda. So sometimes it will be greater than 1, sometimes it will be strictly less than 1. It means that using this direct argument, okay, doesn't allow us to conclude. But it's a good idea to think about this one because sometimes it can work, okay, and it is a good idea. Here it doesn't work. Okay? So first natural way to try to do doesn't work.
If x is even minus, x is 4, and then the sums condition.
So, can you repeat?
Two sums.
To show it's not possible, you have the term, okay, it will be horrible. Okay.
Two sums is the same. Yeah, we can just x is even minus x is 4, and
No. So x is even minus x is what? What is the meaning of this one? You have evens, okay? So you consider difference as difference between sets.
Yeah.
What you will obtain. If you take x is even minus in terms of set x is odd, you will obtain x is even because they are disjunct, both of them. Okay? So be careful, don't make confusion between difference between sets and difference between numbers. Huh? Okay? I mean? If you consider this one minus this one in the terms of sets, you obtain this one. So, I am okay, but it's exactly what I have said before. I am agree that if you want to prove that something is strictly positive, you can prove that the difference is strictly positive. I am okay. But here, if you take the difference between this kind of term, it's not that clever. It's like to do the ratio of sum. If you do the difference between product in general, that's why I prefer to consider the ratio of the general term. You can try to do this, but if you do this, exactly as I have done here, you won't be able to conclude this way. You can try. Okay, but you will see that what I have inside, the sign of the difference of what I have inside will depend on the value of k. So you won't be able to conclude this way.
So in these two cases, beforehand we've realized that those sums were actually series expansions of some specific functions.
Yeah.
And we've seen that instead of having 2k or 2k plus 1, if we had k, that was exactly the series expansion of the exponential function. But in these two cases, where instead of k and we have 2k and 2k plus 1, we also have some series expansion.
Well, suppose that we don't know. I'm agree with you. You have cosinus hyperbolic and sinus hyperbolic. I agree with you, but I consider that you don't know this one. But the idea is not that bad because it's the way we obtain, okay, the expansion of that functions. So, my problem is the following one, in fact. So I erase this. And I keep my computation on the board because we need it. So, what I know, okay, what I know when I work with the Poisson distribution, but the way I have defined the Poisson distribution comes from this fact here. Exponential of x may be defined this way, and it's exactly what the formula that allow me to define the Poisson distribution. Okay? So it means that if I have all the terms inside, okay, I am able to compute it. My problem is to see if it is possible to compute the two related sums that are the one when I consider only the even parts or the even indexes, okay, or the odd ones. Okay? So this one, okay, in fact, this one is the combination of, okay, write it this way. So I am able to compute a priori the sum of these two, but I have to think a little to see what happened for each of them. But this is the idea, to come back, and often it will be the case. For the binomial distribution, you often come back to the formula a plus b to the power n. Okay, for the Poisson, we always come back to the definition of the exponential. As in the case of the geometric, we come back to the sum of the terms of a geometric sequence. Okay. So I have this one. I have the term with 2k and the term with 2k plus 1. So I have to find, in fact, a trick in order to make one of them disappear in order to be able to compute what I want, that is each of them. Okay? So in fact, it's a general trick. Do you have an idea? No idea? I have this one. Any idea? if you are in this kind of situation, if you want to isolate the terms indexed by even indexes or the one indexed by odd indexes, but the idea is to consider f of x and to consider f of minus x. Why? If you take exponential minus x, I have the right to use exactly the same formula. So it will be what? It will be the sum from k equal to 0 to plus infinity. Okay, I have minus x to the power k over k factorial. So I have minus 1 to the power k times x to the power k. And minus 1 to the power k is equal to 1 minus 1, 1 minus 1, 1 minus 1, depending on the fact that I am even or odd. Okay? So if I want to do the same job as here, but if I replace x by minus x, here I have a power that is an even number, so the minus will disappear, and here I have minus 1 to the power 2k plus 1, so I will obtain minus 1. And at the end, if I do exactly the same thing as here, it's the sum from k equal to 0 to plus infinity x 2k over 2k factorial plus the sum from k, or minus in fact, the sum from k equal to 0 to plus infinity x 2k plus 1 over 2k plus 1 factorial. Okay? And I consider that if you have this one, okay, the same idea apply doing what I have done here. You consider f of minus x, and doing sums or difference, you will isolate the term indexed by even numbers or the terms indexed by odd numbers. So if I have remarked this, okay, it is almost finished now. So I keep what I want to compare in the board, okay? I erase my first try here. That doesn't work. Okay, so how can you do if you want to isolate this term from these two formula here? Plus, yeah. So I can write it this way directly. The sum from k equal to 0 to plus infinity x 2k over 2k factorial may be written as what? If I do the sum of both terms, I will make disappear the part indexed by odd numbers, and I will obtain 2 times the sum I am interested in. And it's what we call the hyperbolic cosinus, but whatever. Okay? I have this one. Because if I do the sum of this one and this one, the plus and the minus disappear, and I obtain this sum plus this sum, that is 2 times the sum I am interested in. And if you have understood, okay, for the other part of the sum, what I have to take in order to express the sum indexed by the odd, minus. If I take this one minus this one, I will make disappear the sum I don't want. So it is exponential x minus exponential minus x over 2. Okay? And now it will be not that complicated to do the job because I have the good expression for what I want. And if I come back to the probability I am interested in, that is the probability to be even and the probability to be odd, by just replace the fact that I know the sum of these terms and I know the sum of these terms. So I obtain what? I obtain exponential minus lambda, exponential lambda plus exponential minus lambda over 2. And here I have exponential minus lambda minus exponential minus lambda over 2. Because I just use what are these two sums with my trick of computation. Now it's finished. Because what is the difference between this expression and this one? But the only thing is that I have a minus here and here a plus. And I know that the exponential is a mapping that is positive. So you have always the fact that the first is greater than the other one. Okay? So 3 steps, okay, in this exercise. First, try to express what is to be even and what is to be odd, and then use the sigma additivity. Then I have to compare two sums. The natural idea is to try to compare the general term. Unfortunately, it doesn't work because I don't have a general inequality because I have something that depends on k. So I have to find another ID, and an ID that is in fact that general. That is, if you have this kind of sums with x to the power k, I consider the same with a minus x instead of x, knowing the fact that minus 1 to the power k will change the sign, okay, anytime I change the parity of the number, you obtain what you want. Okay? And here, the inequality I have here is independent of the value of lambda. It always works, okay? Because exponential is a positive number. Okay? So I don't say that is easy. Okay? So what I may expect for you if you don't see, if you see this kind of exercise for the first time, to be able to express these two, to try to compare the general term and to see that it doesn't work. But now, I have given to you a trick in order, when you have a sum with inside x to the power k, to be able to extract something that is indexed by the even numbers and something that is indexed by the odd ones. And the idea is to consider this one and the same one with the minus x instead of x. Okay? Do you have questions? So, not that easy if I don't know this trick, but from now on, it's something that is classical for you. Yes?
I just want to make sure I'm reading that symbol right, that even is greater than odd. That's what the...
Even it's tricky here. Huh? Because, yes,
Okay,
even is tricky greater than odd.
I just want to make sure.
Yeah, it's what I want to prove, huh? Look at the board. But it's a strict here because exponential here is a strictly positive number. So what I have said here, okay, in fact I have a little bit more because I have a strictly positive number here with a minus and here a plus. So this one is strictly greater than this one. Exactly what I want to prove. Okay, thank you. Questions? So I repeat that at least be able to do this for the moment. Okay? That is to be able to decompose this kind of even, okay, in order to use the hypothesis of the statement. Okay. If you don't have questions, next exercise. So the next exercise is related to a remark I have done in the case of the definition of the Poisson distribution. For the Bernoulli, the binomial, the geometric, and the uniform, I have given to you example taken from the real life. For example, the uniform, you roll a dice, okay? Bernoulli, you flip a coin. Binomial, you flip a coin independently several times, and you count the number of heads, for example. And for the geometric, you flip a coin, okay, until you obtain the first head, let's say, and you obtain this way a geometry. For the Poisson, I wasn't able to to give you a real life example. But here we are going to see, in fact, that the Poisson distribution may be seen as an approximation of the binomial for particular values of the parameter n and p. Okay? So just be careful because there is a little misprint in the statement of the exercise. That is the exercise 8 here. This one. Okay? I have this. So what is the statement? So I consider a binomial, probability of success small p, number of trials small n, as I have explained to you intuitively, and I define lambda as p times n. Why not? Okay? Show that, well, in fact, the probability that my binomial is equal to k, success, it's like I flip a coin, I am interested in obtaining head, it's the number of head I obtain. It's what I mean by success in the case of a binomial. So the probability that my binomial is equal to k is equal to this expression. Okay? So it's the first thing we are going to see. And then it's here that I have a misprint. Because why this is completely stupid to write this? No, not equal to 1. No, P is the probability. It's a number between 0 and 1. So if I want to make it goes to plus infinity, little bit complicated, okay? It's 0 that you have to replace here. It's P goes to 0. P goes to 0, not to plus infinity. The approximation we are going to obtain is an approximation for big N and small p. Okay? A big number of trials with a probability of success that is small. Okay? But for the moment, before to pass to the limit and to obtain what I want here, just try to obtain this one. I give you 2 minutes to do, because if you know the definition of a binomial, it takes you 1 minute to do. Okay? So I erase the board, okay? Write the statement. I repeat that you just have to write what is the definition of a binomial. And from this definition, try to express the probability that a binomial is equal to k with this form here, using the fact that lambda is defined to be p times n. Okay? So it's the exercise 8. My hypothesis is that x follows a binomial of parameter n p. What is the probability that x is equal to k from the course? If you don't know, of course, you are not able to do the exercise. What is this?
P and K.
Yeah?
PK.
Yeah.
1 minus P. N minus
I'm sure that you are able to read. You know?
yeah.
Sure, huh? But you have to know this. Huh? You have 5 in the discrete case, and you will have 4 in the continuous case to know. 5 also in the continuous case. Bernoulli, binomial, Poisson, géométrique, uniform. Not all the other distributions that exist will be considered as new, not in the course, okay? But I want you to know things about these 5 ones, their expectations, and their variances, and so on. Okay? So I have this. And I want you to express this one on this form here. Okay? And what is the lambda? Lambda is just n times p. It's a notation introduced in the statement. So you take picture of the definition of a binomial. You have it in the slide, huh? Okay? Take a picture of me. Yeah. It was a joke. Have you tried to have a look on the videos I have done or not? It works? I think it's not perfect, for sure. But okay, with the material we have, okay, it's not that bad, I think. Okay? But typically, if you are able to follow the course this way and you have a video as a support, okay, it's perfect. If you have only the video, maybe it's going to be a little bit more complicated. But I hope that we will never be in this situation. Okay. So what ID? In fact, no idea to have. Just replace. So first I see that I have no more C and K here. It means that I have to use the definition of what is C and K, okay, with the factorial. So I will write it here. Probability that x is equal to k. What is C and K definition? So you need, I repeat, to know the definition from the course, from one session to another, or you will have some problem for sure. So what is this? This one, okay? So I have this one, then I have p to the power k, but I don't have p in this expression here. So it means that I have to replace by this expression because I don't have p what I want. And p here is just equal to lambda over n. So I replace, okay? Lambda over n to the power k. And here, exactly the same. I have p inside this expression, but when I have a look on my statement, I don't have p. So I replace by lambda over n to the power n minus k. Okay? So, we are going to do step by step. I know what I want to obtain. I have this one. So first we are going to try to have a look on the terms I have already in this expression. So I have k factorial here. I'm happy because I have k factorial here. Okay? So I keep it. I have lambda to the power k. I am happy because I have here lambda to the power k. For the other ones, okay. But if I have a look on the last, 1 minus lambda over n to the power minus k, this is this one. Okay? So just copy what I remark to be exactly what I have in my sums here. Here I have lambda to the power k over k factorial. I have 1 minus lambda over n to the power minus k, and it remains term that I have to handle with. I have n factorial over n minus k factorial, and I have 1 minus lambda over n to the power n over n to the power k. Okay? So the idea is not to try to do everything at the same time, just see, okay, in the statement I am happy because I have the answer, I have exactly what I have to prove. The the question is not just to prove the second step. I have an intermediate question here. Yeah.
We have 1 minus lambda over m.
So I have n factorial here, n minus k factorial here. I have n over n k, and I have 1 minus lambda over n to the power n. What is your problem?
In the expression
We have the same
power n first.
1 minus lambda over m power m.
Yeah. It's exactly what is coming
We
from.
already have in the equality of the slide. 1 minus lambda.
Ah, yeah. Okay. Yeah, you're right. Okay. So you do step by step, but quicker than me. So here, I'm agree with you that this term here is here. Okay? So I can remark it. So let's continue. Lambda k, 1 minus lambda n minus k, y minus lambda over n, and I have over k factorial. So it remains to handle what I have in white here in this expression, okay, and to obtain the other terms that are these ones here. What is n factorial over n minus k factorial? So keep in mind that n factorial is the product of the n first natural numbers, okay, or integers. So I have 1 times 2 times 3 times 4 until time n. N minus k factorial is what? It's 1 times 2 times 3 times 4 until time n minus k. So I will have a lot of simplifications, in fact. But all these terms here, okay, are contained in this product here. So at the end, I obtain n factorial over n minus k factorial. So let's write it. It's n times n minus 1, n minus 2 until 1 divided by n minus k times 1. And here, if I want to be a little bit more precise, I can write it this way. I have here n minus k, that is here, okay, and I have n minus k minus 1 from 1. Okay, and here before I have n minus k plus 1 here. Okay, so here I have just written for the moment n factorial over n minus k factorial. Just using the definition of what is n factorial and what is n minus k factorial, and I have to divide by 1 over n to the power k. So you see that I have a lot of simplifications here. I can simplify all these terms. And it remains n times n minus 1 times n minus 2 times n minus k plus 1, okay, divided by n to the power k. So I have lambda to the power k, 1 minus lambda over n minus k, 1 minus lambda over n over k factorial. Then I have, okay, n times n minus 1 until n minus k plus 1 divided by n to the power k. How many terms in this product here? K terms, exactly k terms. It's 0 minus k plus 1. Okay, so I have exactly k terms in this product. And here, when I do n to the power k, it's n times n times n times n k times. So it means that I can associate to any term here a 1 over n coming from this expression here. So I will obtain n over n minus 1 over n minus 2 over n minus k plus 1 over n over n is the one you have, the n over n you have here, n minus 1 over n is the term you have here, until n minus k plus 1 over n you have in this expression. So I have, okay, until so I have the expression I want. So here the methodology is to say, okay, I have a big expression here. Don't try to do everything at the same time. Make appear the things little by little, starting from the definition of this one, and try to make appear one term by one term, okay? In fact, it's not that complicated. I just have to know the definition of what is a binomial and the definition of factorial. Okay? And I obtain exactly here what I have in my statement here. Do you agree? So to know the definition of the binomial and to know the definition of factorial give you, working a little, okay, what I have here. Do you have some questions? Okay?
We would go, I'm not sure if it's correct, but if we would compute limit.
For the moment, I don't speak about limit. I just want to be sure that it's okay for everybody. Okay? After I will come back to the limit point. You will do your remark, okay, but just after one second. Everybody is okay with this one? In the way I obtain? Yes? If you say nothing, I consider that it is a yes. Huh? I am not in your brains. Okay? So, your remark.
Yes, I wanted to ask if I calculate the limit. I'm not sure. Would I get the same result with n going to infinity
Yeah.
from this expression?
So, keep in mind that I have said to you that I have a misprint in my. So its p goes to 0.
I know, I'm asking.
Yeah. So its p goes to 0, and you have a second indication. P goes to 0 and lambda remains constant.
Okay.
Lambda remains constant means that if n goes to 0, what is the limit of n? You don't have the right, and you don't have the choice. If p goes to 0, n has to go to plus infinity because lambda is a constant. So it means, for example, that you can take p equal to, I don't know, 2 over n. And yes, and in this case, lambda is equal to 2. Okay? It means that the behavior of n is lambda over p, with p that goes to 0, meaning that n goes to plus infinity because lambda is strictly positive. Okay? So have you understood his remark? Just say that. So I repeat, there is a misprint in my statement here. My p goes to 0, not goes to plus infinity. And I have a second indication that is p change so that lambda remains constant. It means that lambda is a number here. And lambda is equal to p times n. If p goes to 0, I don't have the choice. Lambda goes to plus infinity. If p goes to 0, n goes to plus infinity. I don't have the choice. Okay? So, if I translate my statement, it means what is the limit of this one when n goes to plus infinity? Because in this expression I don't have p, my lambda is fixed, so I won't change it, and my n goes to plus infinity. Okay? So my question here is just what happened to this expression when n goes to plus infinity, and the objective is to obtain the general term of a Poisson distribution. So once again, we are going to see, so if I have a look on my limit I want to obtain, I have already this term here, that is lambda k over k factorial. So I won't touch it, okay? I have it already. So I am already happy to have this one here. So I have to deal with the other terms. Okay? I can take them one by one if you want. Okay? What happened for this one? Yes. What happened for this one when n goes to plus infinity? 0, no. 1, because I have a polynomial in n if you want here and the same below. So I just have to focus on the term of higher order, that is n here. So this one over this one goes to 1 when n goes to plus infinity. In fact, the same will happen for the other term, and for this one, I doesn't go to 1, I am equal to 1. It's the limit case. So all these terms here goes to 1. Clear for everybody? Because k is fixed. Okay. So this one goes to 1. Because I have k terms, k being fixed, such that if each of them goes to 1. So for this one it's okay. For this one here, and for this one. So they look like the same, but they are not. And there is a major difference between them. So what do you think about this one here? So what is the limit of lambda over n? What is the limit of 1 minus lambda over n? What is the limit of 1 to the power n? So the limit of this one is, it doesn't work. It doesn't work. Why? Because, so I come back to the reasoning I have tried to do. So lambda over n goes to 0 for sure. 1 minus lambda over n goes to 1. But in fact, I don't have 1 inside. I have something that goes to 1. That is close to. Okay? And if you take a calculator, for example, you take, I don't know, 0.999999 and you put it to the power, let's say, 1000 billion. You will see that you won't obtain a 1 in fact. Okay? Because inside here, you have this term that goes to 1, but the power is also moving. Contrary to what happened here, because here, my reasoning works. Lambda over n goes to 0, 1 minus lambda over n goes to 1, and I have a fixed power here. Okay, let's say square, cube, or something like this. And this way it works, because my k is fixed, and if you take, okay, the power k function is continuous, so if I have something inside that goes to 1, if I take the power, I will obtain 1. So you see the difference between both terms. Here I have k that is a number that is fixed, and here when I consider the limit, n goes to plus infinity, while what I have inside goes to 1. And a priori, I can't say anything except if I remind, okay, what is this limit? So are you okay that this term goes to 1? Are you okay? Repeat my reasoning. Lambda over n goes to 0, 1 minus lambda over n equals to 1, and I have something to a fixed power. Here, I am not able to do the same reasoning because my n is moving. So my question is the following. It's something that I hope that you have already seen one time. Okay, maybe you have forgotten, but what is the limit? 1 plus x over n to the power n. It may be one definition of the exponential. This converges to our exponential of x. The idea, if you want to show why this limit is this one, you say that 1 plus x over n to the power n is equal to the expectation, the exponential of the logarithm of the same quantity. You know the property of the logarithm with respect to the product of power, so it's exponential n, the logarithm of 1 plus x over n. And if you do a Taylor expansion at the other one of the logarithm of 1 plus x over n, because x over n goes to 0, you obtain that this is, let's say, equivalent to exponential of x when n goes to plus infinity. So you have to know this kind of limit. Typically, why you have to know? Not just for this kind of exercise. Or oops. Ah yes, I have. Not for this kind of exercise here, but because in finance you will see that if you consider interest rate modeling and the way to capitalize or something like this, if you pass from discrete time to continuous time, you will explain why you have the convention of exponential of r when you want to capitalize or borrow something to a bank. So it's a limit that is that's known, and typically because in the course of finance, for sure with Miss Nago, you know that you are going to do this kind of things. It's finished now, okay? Because if I have this in mind, what I have done here, 1 minus lambda over n to the power n, it goes to exponential minus lambda, and at the end, I obtain that when n goes to plus infinity, the probability that x is equal to k is equal to lambda to the power k over k factorial exponential minus lambda, meaning that when n is big, when p is small, n times p being constant, I can say that for large n, a binomial distribution of parameter np may be approximated by a Poisson of parameter lambda. Okay? And in real life, in general, it's the way a Poisson arrives as an approximation. So you have a binomial, in fact, but for a very big n and very small p, okay, and you can approximate it by this Poisson. Okay? And in general, because from a computational point of view, okay, these kind of terms are easier to compute than the CNK, typically when n is very, very, very big. So we have a trick in order to compute the CNK, okay, it's what we call the triangle Pascal, and the Pascal triangle, but it's okay if you want to compute for n equal to 5, 6, 7, 8, or 9, okay, but if you want to compute CNK for n equal to 1 billion thousand, typically what can happen in statistical physics or statistical mechanics, okay, with a computer, even with a very big computer, it can be very complicated to compute CNK. That's why we prefer to use this approximation that is easier to compute and that is in practice not that bad. Okay? So, if you have to keep in mind something from this exercise, when I have a binomial with big N, small p, n times p being constant, I can approximate by a Poisson. Okay? Do you have questions? Okay, so from now on, okay, you have a kind of interpretation of the Poisson as an approximation of the binomial. Questions? No? So I continue if you don't have. I try to do by yourself the exercise 10. So I read the statement with you. So I have a tool gate with m counters, okay? Let capital M be the number of cars arriving in 1 hour, and I suppose it's an hypothesis that this number of cars follows a Poisson distribution of parameter lambda. Okay? The drivers choose randomly and independently a counter. We denote by xi the number of cars which passed at the counter I. I want you to compute this conditional probability, and I want you to find the expectation, and V is for the variance here, the variance of xi. So let's do a little picture, and then I want you to think about this. So it's the exercise 10. So I have m counters. Okay, so I can represent the situation counter 1 until counter m. Okay, here you have the counter you are interested in, that is the counter I. You have a car. Since I have color, it will be a red car that arrived. That nice car, okay, this way. So it arrives, and we suppose that you choose randomly a counter, okay, and independently. So you have car this way, one by one, okay, they are going to choose randomly a counter, okay, 1, 2, or I or M, okay, and this is done randomly. And the number of car I have here follows a Poisson distribution of parameter lambda. Of course, it is not fixed. It depends on the okay, it depends on the months, okay, it depends on the days. But we suppose that it is a Poisson of parameter lambda. Okay. So you have everything in order to try to compute. So have you understood the situation? You have understood? That's exactly what it is explained here. And I am interested in the number of cars that choose this counter here. Okay? 5 minutes in order to try to think about it. If you have some questions, ask me. If you know your quotes, okay, the answer should be 5 seconds to compute this probability. A little remark. Are capital N and Xi independent? Yes? Where it is taken from, this? No. What you do here is that the drivers choose randomly and independently a counter. Okay? So it means that what happened for each car here is independent. It is the meaning of the statement. Okay? So it doesn't mean that the number of cars is independent on the Xi. Can you find the relation between capital N and the Xi? Capital N is the total number of cars. X1 is the number of cars that choose the counter 1. X2, the number of cars that choose the counter 2. Xm, the number of cars that choose the counter M. Yeah, I have capital N, that is X1 plus Xm. So it will be very complicated for you to obtain something that to obtain that xi and capital N are independent. Because in the expression of capital N, you have capital Xi that is inside. Okay, so they are not independent. They are not independent for sure. So since they are not independent, it means that this conditional probability is really a conditional probability. Okay? Because if they were independent, conditional probability is just the probability that Xi is equal to K. But it's not what I have here. Of course, the number of cars that choose number, find the counter number I, depend on the total number of cars I have at the beginning. Okay, so try to think. So try to think to this situation and what concretely happened before to try to compute something. What do you do concretely when you want to compute xi in real life? So, you have a look on the cars. You have, let's say, the first car. It chooses or not. If it chooses, one more. For the second, the same happen, and so on and so on. It's the way that you count. Okay? So try to translate what I have said here in terms of probabilities or in terms of random variables. An ID? Capital N is a random variable, it's not a number. have a very, very basic situation here to obtain Poisson. Not complicated to obtain this.
Why is
But I repeat, what is your argument?
because the average of each one
I have never defined okay, a Poisson as an average of something.
but one is the average.
Lambda is
Is the average also.
it's the average of capital M, yes. Well, I don't say that it's false, I say that I miss the argument here. And typically, what I want you to compute is not this one first. Huh? Keep in mind that I first ask you to compute this conditional probability, and then in the second step, I want something that is related to the distribution of this side, so that will be related to this one. Okay? So I don't say that your answer is false, I say that I miss the argument here. So intuitively, I think that you have the thing, but you need to explain.
Because the third is the average and the average are going to be distributed here. And so the average of this equation is the average of this.
So the situation you have is okay. So if I translate what you say, I have x1, x2, xn, okay, that have the same distribution, let's say. Yeah. They are the same, they are independent. Are they independent? Something that is a little bit more complicated to say here because the sum of all of them, okay, is equal to something with the normal distribution. But so you do like an average of a Poisson and you want that all the terms of the sum, okay, is the Poisson of a parameter that is the average of the parameter. So it's not that you have so in default, typically first, you have a preliminary question that is compute this one.
If I do this as an average,
Yes, but the fact is you don't have to. If I am able to do this, you will be able to do this. That's why I have done my little picture, because in order to compute the conditional probability we are going to use vested in, we are not going to use the definition of P of A given B equal to P of A intersected with B over P of B. It's not what we are going to use. We are going to use the particular situation we work with here. Okay? And in fact, I said that this situation is a situation we have already seen together, not exactly with cars and counters, okay? Not with cars and counters. So what is my situation? One car arrives, it chooses or not. Another car arrives, it chooses or not. A third arrives, it chooses or not. So it means that I repeat things independently because the drivers choose randomly and independently a counter. And for each car, I choose or not. Choose not. Okay? So it is a random experiment with two issues. The one that interests me is to choose counter I, because it's what I want to count here. So in which situation we are taking from the course. You repeat something, okay, and you have, let's say, one success. Hmm? No. Binomial. I repeat n time flipping a coin, and I count how many head. It's exactly the same here. You repeat small n time because you have small n car. If you are given capital N equal to small n, you have small n car that arrive. Okay? Each one choose or not. So, in order to explain, okay, from what we have seen together, I think it's the clearest way, we can say this one. I define Z1, a random variable. It's just to explain in a very short way this way. So this is something that is related to the car number 1. I said that Z1 will be 1 if you choose the good counter and 0 otherwise. Okay? What is the distribution of Z1? I'm sorry, with the mask, with the noise of the street, okay? So if you want me to listen to you, you need to speak louder. Bernoulli. Bernoulli? Yes. 1, 0. And if I want to describe perfectly my Bernoulli, what is the parameter? P, yes, but what is P? Huh? So, yeah? So, I say that I choose randomly. Okay, so I choose 1 among n. Okay, and randomly. It's a Bernoulli of parameter 1 over m. I choose, I don't, I choose, I don't, I choose, I don't. The probability that I choose is the counter I am interested in, that is one single counter over the total number of counters, that is small m. So I have a Bernoulli of parameter p. So Z1 is this one, and if you have understood, I can define exactly in the same way Z1, Z2, Zn. Okay, if I have small n cars as in the statement of question A, I have small n cars here. And what is what I am interested in? Xi is equal to what? So Xi is exactly the number of cars which pass at the counter I. If you have Z1, Z2, Zn, how can you define excuse me, I have done a mistake here. So what I have written is true here, but it's not what I am interested in. I am interested in counter I here. Counter I. Here, it's the counter I that is fixed here. Okay? So Z1, 1 if car 1 chooses counter I, Z2, 1 if car 2 chooses counter I, and so on. Okay? So if I define Z1, Z2, Zn this way, just changing the number of the car here, are you able to express Xi in terms of the random variable I have defined here? You want to count. This one tell you 1 if I pass, 0 otherwise. Z2, 1 if the second pass, 0 otherwise. If you want to count all of them, yeah? Items?
1 over n.
What is items? No, just repeat my question. From these things that allow me, in fact, to know if they pass or not, if I want to express the total number of cars that pass counter I, are you able to express this quantity using this random variable here? If yes, what is the relation? xi doesn't follow binomial. My question is the following. So here, z1 equal to 1, okay, if car1 chooses counter I. z2 is equal to 1 if car2 chooses counter I. z3 is equal to 1 if car3 chooses counter I. My question is, are you able to express xi, that is, the number of cars which pass at the counter I using this random variable here? Yes, so, so you answer to the next step. I want the first step. Okay? So I can write it this way. So if I know that capital N is equal to small n, so if I know that my capital N here is equal to small n, and it's exactly the situation I am in question small a, I know that capital N is equal to small n. The number of cars that pass at the counter I is equal to this. Z1 plus Z2 plus Zn. Count the total number is just to say 1 if it passes or not, 0 otherwise, 1 if it passes 0, if you do the sum. Okay? I repeat, it's exactly the way you count. If your job is to count the number of cars, it will be exactly what you will do. One car arrives, okay, 1 if it passes, 0 otherwise, 1, 0, and you do the sum at the end to be sure to have the total number of them. So, each of them follow the bandwidth of parameter 1 over m. Okay? What can I say about these random variables? I can say that I know that the drivers choose randomly and independently. Independently means that these random variables are independent and all have the same distribution to be a Bernoulli of parameter 1 over m. So what will be the distribution of this one? You have the sum of n independent Bernoulli of parameter 1 over m. So you have a binomial of parameter n over m. So you are typically in the situation where you repeat independently the same experiment. Each experiment has a success or not, that is here to pass counter I or not, and you want to count the number of success. So in the example from the course, you flip a coin n times. Success means for me to obtain an head, and I want to count the number of heads. It's exactly what you do here. If you replace to obtain head by to pass to the counter I, and you do this n times independently. Okay? So when I know that the total number of cars is equal to small n, okay, I am able to express xi this way. Okay? And so I am able to compute this one. It's just coming from the definition of a binomial of parameter n and 1 over m. So the probability that xi is equal to k given capital N is equal to small n is equal to what? Well, it's exactly what I have here. It is equal to, so it's a bn 1 over m. So you have cn k 1 over m to the power k 1 minus 1 over m to the power n minus k, and this is true for k between 0 and n. Of course, it's not possible to have more or less cars that pass to the counter I than the total number of cars. Okay? So here, typically, it's not a computation that you have to do. It's to understand the situation and just to say, okay, I have classical distribution in the course. Which one here appears, let's say, that naturally in this situation? I repeat independently the same thing that have two issues. When you are in this situation, often the binomial will arise. Questions? So, if you have understood this, it's finished. Huh? So the only question, in fact, is have you understood this one? That is, have you understood how to count cars? Concretely. Questions? Questions? No?
We are using the Poisson distribution just to get small n.
No. For the moment, okay, I have never used the fact that capital N follows the Poisson distribution. Nowhere. Be patient, you have the second question. Okay? So here, if I change this hypothesis by what you want, of course I obtain exactly the same thing. Okay? It's not the distribution of capital N that have an influence on this conditional probability. The only thing that interests me is that I have small n cars arriving. And then repetition of n experiment independently, okay, with success or not. Other questions? No? Yeah?
Can we consider the number of k according to binomial for large n and small p? Which this assessment?
Which one?
Can we consider?
No?
For
No. No, because, okay, you don't know. I have said nothing about the fact that M is big, N is big. I don't know. No. The approximation of a binomial by a Poisson, okay, is in the case where the number of trials is big. And here, a priori, what I have proved here is for any n. So n can be equal to 2 or 3 or 1. Okay. And p small. And here, I don't know. If I have only 2 counters, well, p is not small. If you have 1 billion counters, okay, yes, but in real life, it's not what you have.
If I assume.
If you assume, you don't do the same exercise.
If I assume I also have the same.
Yeah, I agree. So you can assume, but it means that it's not the exercise 10, it's your exercise 10. And in general, okay, typically for the midterm and the final, it's my exercise that I want you to solve, not yours. Okay? So, if you don't know what to say, maybe yes, it's interesting because you know something in the course, you say, if I suppose a little bit more, I am able to do, why not? But you won't have all the points. But if you say something that is clever, even you had a little hypothesis, but maybe I will give you a little something. Okay? But I want to do the same exercise without supposing extra hypothesis than the one I have here. Okay? And typically, to come back to your point, if I suppose that capital N follows a Poisson, it means that capital N takes the value 0, or 1, or 2, or 3, or 4, 5. It means that it can take small values, big values, average value. Okay? So supposing that N is big, is a strong hypothesis here that is not true in great generality. Okay? So be careful, huh? I repeat for everybody that you have the hypothesis of the statements. If you add hypothesis, why not? But it won't be the same exercise. Okay? If you need more to solve, in general, it's not what I am expecting from you. Okay? Because a priori, if the statement is clear and okay, I hope that I won't miss anything in order to allow you to do the exercise without supposing anything. Okay? Okay?
Yeah, just one question.
Yeah.
I think I understand it. This condition that n equals n, it asphyxiates the n to n. That's,
Here,
that's
it's fixed.
literally what it means.
In this
that's
question?
that's why I can only, okay.
Yeah, of course. When you want to compute this one, you consider capital N equal to small n. So capital N equal to 2, capital N equal to 3, or a fixed n, of course. In the second question, we are going to make this n moves. Because I know that n can take any kind of value, 1, 2, 3, 0. So, once again, I have asked you to compute first this conditional probability, and we have it here. We have this one here. Okay, I have done the job. Now I want you to compute the expectation. Excuse me. Yes. Now I ask you to compute the expectation and the variance of xi. So, in general, under which condition you are able to compute the expectation or the variance? But if you know the distribution, okay? So a natural way to do is to try to find the distribution of xi in order to be able to compute the expectation and the variance. Why it's not that bad to do this? Because suppose, for example, I don't know for the moment, but suppose that the distribution you are going to find for xi is a distribution from the course. Binomial, Bernoulli, a Poisson, a geometric, or something like this. The exercise will be finished. Because in the course you will know that if I have something, my expectation, my variance will be. Okay? And it's something that you have to think about every time, that when I ask you to compute an expectation and a variance, the very first step should be, is it something from the course? Yes, no. So it's a Bernoulli, yes, no. Okay? If yes, I use my course and it's finished, perfect. I don't have to do any kind of computation because it's a result from my course. So in general, something that I prefer to do, okay? Other hypothesis, it's no, and now I have to compute directly, okay, the things, and I can't use the result from the course, okay? So, to compute the expectation and the variance, we are going to try to compute the distribution of xi. Okay? So I erase my little picture. So first, what are possible values for xi? From 1 to n. 0. From 0 to? Yes, so it's capital N. Don't forget that in the question A, I know the number of cars, small n, but a priori I don't know it. Capital N, the number of cars is just a Poisson, so it means it can be anything from, yes?
Why is it 0 to A?
What is?
Why is it 0 to A?
It's exactly what I have said, that the number of cars that arrive, it was my previous picture here, follows a Poisson distribution of parameter lambda. So it can be any number in capital N.
No, my question was for B, you said we're going to consider 0 to infinity. Why not 0 to n?
What is N? Yes, but N is a random variable. Because if I tell you, okay, I consider as capital N the number of cars that I am able to see in the window. Right? It will depend on the days. If you are on Sunday, less, I suppose. Okay? So capital N is a random variable, so you don't know a priori what is the number of cars that will arrive, let's say, each hour here. But you suppose that this quantity you don't know is a random variable following a Poisson distribution of parameter lambda. So you can take values in capital N, not a single one. Okay? So xi of omega is n. Okay, because capital N is a Poisson distribution of parameter lambda. So if I want to know the distribution of xi, you have to compute the following. So what interests me is the probability that xi equal to k, and I want you to compute this one for any k belonging to n. It's my job. Okay? That is to find the distribution of xi, and I will have two situations. If I obtain here something that is known, I will be very happy, because in order to compute the expectation of the variance and the variance, it will be very simple. But if I don't obtain something that is classical, I will have to compute the expectation from the definition and the variance from the definition. Okay? So you have two questions, A and B. B, that is related to this one. Okay, so I want to compute this probability, and I have computed this one. Do you think about a result from the course? The result, the only result that makes the link between we are going to do the break in 5 minutes, so if it's very, very urgent, you can go, or just be patient. In 5 minutes, it will be okay. Oh yeah, I don't have see the clock. Yes, I will do the break. I just finish with this word here, and after we are going to do the break. So I have conditional probabilities. I have a probability to compute, and I see that here I have exactly what I have here. So which result from the course? Law of total probability. Yeah, it's the only result you have concerning this. Law of total probability. But keep in mind that if you want to use the law of total probability, you need a partition of the universe. What will be the partition of the universe? These events here. The number of cars. It can be 0, or 1, or 2, or 3, and so on. So all these events here that are the possible values of capital N are a partition of the universe. And so, using the law of total probability, and the justification is that these events here are a partition of the universe. I use the law of total probability, and that's why I have made you compute this conditional probability first, because it was not that complicated to compute it from the fact that I recognize the binomial situation. Okay? And then to compute the expectation and the variance, I compute the distribution of xi, and then I am able to deduce the probability I am interested in from all the conditional probability I have previously computed. And you have everything here, because you know this one from what I have written here, and you know the probability that capital N is equal to small n, because you have an assumption on the distribution of capital N. Okay? I break now, and after I will do the computation. Okay, so I have now to compute this sum coming from the law of total probability in order to try to find the distribution of xi. Okay? So I have just to plug in this formula what I have obtained from the previous question. And from the previous question, we have seen that we have this, that the conditional probability that xi is equal to k given that capital N is equal to small n is equal to this expression, but be careful if k is between 0 and n. Of course, it's not possible for the number of cars that pass at the counter I to be greater than the total number of cars. Okay, so I have this restriction on Kn. So, if I write the probability I am interested in, I see that these conditional probabilities will be 0 if I don't check this. So it means that since my sum is over n, my n has to be greater than k. Okay? Because if it's not the case, I obtain 0 for sure. So my sum starts from k. Please, okay. Starts from k to plus infinity. This conditional probability is equal to this term here, C n k, 1 over m to the power k. Be careful with the door because you have noise and you will have noise on the videos. So I don't mind, I won't see my own videos, okay, but it's for you, okay? I have too much film to see, so I won't see my video. For sure. Maybe you will be in the same situation. I don't hope so. So for the moment, the only thing I have copied is that this conditional probability here is equal to this one, but be careful when k is greater than n, or equivalently when n is greater than k, that's why my sum starts from k here. Okay? And then I have to multiply by what? Be careful with the door. So first 10 minutes, not a quarter. And secondly, be careful with the door or the video. Okay. And it remains to write this term here. And this term comes from the statement because I know that capital N follows the Poisson of parameter lambda. Okay, and now we are going to use the fact that capital N follows the Poisson of parameter lambda, that is here. Now I have used this one, I can erase. I multiply by the probability that the Poisson is equal to n, that is exponential minus lambda, lambda to the power n, over n factorial. Okay? So I have this big sum to compute. Why not? So, once again, instead of trying to compute everything at the same time, okay, we are going to try to do this with methodology. So first, it's a sum over n. It means that all the terms that doesn't depend on n can be removed from the sum. Okay? So this one depends on n. So the break is 10 minutes, huh? If you late. So I can remove all the terms that are not depending on n. This one depends, this one doesn't, this one depends, this one doesn't, and depends. Okay? So a priori, for the moment, I can I have this one over m to the power k, and I have a sum from n equal to k to plus infinity of c and k, 1 minus 1 over m to the power n minus k, lambda to the power n over n factorial. So what can I do now? So keep in mind that I have c and k here, but it's an infinite sum, so it means that it won't be possible for me to use the formula as a plus b to the power n equal, because I have an infinite sum. So it's not this one that we are going to use in order to compute. But I see that I have here n factorial and I have my c and k here. So I can do simplifications, because okay, this term is equal to n factorial over n minus k factorial, k factorial. So I can simplify this one with this one, and here I have something that doesn't depend on n, the 1 over k factorial. So I continue, exponential minus lambda over m to the power k, k factorial, and the sum from n equal to k plus infinity of what? Of 1 over n minus k factorial, 1 minus 1 over n minus k, lambda to the power n. Okay? Next idea. How to continue? So it's a sum over n. When I see this, I say that, okay, in the course we have seen, let's say, two infinite sums. The one that is related to the exponential, okay, and the one that is related to the geometric distribution, and both of them are sums starting from 0. And here I have a sum starting from k. Okay, and I have here n minus k, so I think that yes, I can change my index to see what happened. Okay, in order to simplify a little bit the fact that I have here n minus k and here minus k, and that I start my sum from n equal to k. So I change my index, that is, I change n minus k into n, meaning that instead, so if I replace my index n by this new one here, instead of starting from k, I will start from 0. And that's why I do the job. Okay? So I change my index here, and if I do the job, it's the sum from n equal to 0 to plus infinity, 1 over n factorial, 1 minus 1 over m n, and I have lambda to the power what? N plus k. I change, okay, n into n minus k, meaning that I have here n plus k. My new index becomes n minus k. And I start my sum from 0, replacing, okay, this index by this new one. Do you agree? It's a classical basic change of index, as we have already done. So once again, I see that here I have a term that doesn't depend on n, so I can remove it, okay? And I obtain, we continue, exponential minus lambda, lambda to the power k, over m to the power k, k factorial. sum from n equal to 0 to plus infinity of what? Of 1 over n factorial, 1 minus 1 over m to the power n, lambda to the power n. And now, a priori, you have to recognize something. I have two sums in the course for the moment, okay? The one related to the exponential and the one related to the geometric distribution. I have the n factorial here, okay? So it looks like more something related to the exponential. And in fact, this is an exponential, this one. Because I have 1 over n factorial, and I have in fact 1 minus 1 over m time lambda to the power n. So this is just the exponential of 1 minus 1 over m time lambda. I repeat. You know this. Okay? So it's exactly what I have here, with a x that is equal to 1 minus 1 over m time lambda. So if I continue my computation, exponential minus lambda, lambda to the power k over m to the power k, k factorial, and this sum that becomes an exponential of 1 minus 1 over n time lambda. Okay, now it's almost finished. We are going to try to simplify a little if it's possible. I see that I have still one simplification here. I can simplify the exponential minus lambda with the lambda coming from the first factor here. So this one and this one disappear. And at the end, I finish just here. At the end, the probability that xi is equal to k can be written this way. Exponential minus lambda over m. Okay. Lambda over m to the power k over k factorial. And so, what is the distribution of xi? You have something from the course. What is the distribution I have written on the board here? It's a Poisson. With which parameter? Which parameter? Hmm? Yeah. This one. And the exercise is finished, because now, from the course, keep in mind that what I want the expectation and the variance. Well, I have a Poisson. I know that the expectation is equal to the variance, is equal to lambda over m, equal to the parameter. Okay? For a Poisson distribution of parameter, lambda, the expectation and the variance are the parameter itself. And so, from this one, I have answer to my question, that is to find the expectation and the variance. Okay? So this computation is a little bit long, but once again, okay, I do it step by step. I don't try to find something at the beginning. I remove the terms that doesn't depend on A. I simplify the C and K with the n factorial, and then I see, okay, I have a sum starting from K. I change my index in order to make it's a sum starting from 0, and after I recognize, if I know my course, something that is related to a sum we have already used together. Okay? And fortunately, here, the distribution I obtain for xi is something that is in the course, so the expectation and the variance are computed easily from this one. Okay? So more than this computation, okay, a natural way to pass from this one to this one is to try to compute the distribution of xi and to say, okay, I know these conditional probabilities, and in the course, a result that allow me to pass from conditional probabilities to probability is the law of total probability. Okay, so I have a partition and I can use this law of total probability in this situation. Okay? And that's why I have the hypothesis to be a Poisson here, because since I have a Poisson, I have this nice result at the end. You can do exactly the same exercise with other thing than Poisson. You will obtain the same conditional probability, but when you are going to compute this sum, if you change the Poisson hypothesis into another one, it would be a little bit more complicated to compute, nor impossible, in fact, to compute concretely. And okay. Typically, if you put for capital N a geometric, let's say, I'm not sure that you are able to do the computation. Maybe you are. It will be complicated. I'm not sure that you have a nice formula in the case where you replace the Poisson hypothesis by a geometric one. Okay? Questions? So more than the result, okay, you see the way I compute. Step by step. I don't want to do everything at the same time. Okay? Because if you do this, you will do nothing. Okay? Yeah? No, be careful, huh? Okay? Here, it was my first hypothesis in the course, the way I write the N and the way I write the M. Okay? Here, you have a, so I am with you that I have chosen an exercise where you have small n and small n, so something that is terrible for me. Okay? But here, I have repeat, huh? N, M. So here, you have n, and here it's m, m. Okay? So you have n, 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 m, m.
Wait, when you check index?
No, I repeat. Here, when you change the index, you change the index n. And you have n here, 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 and here. Not here and here, because it's a m here. Okay? In general, I prefer to use different parameters, but I have taken this exercise from a book, so it's probably. But listen to me. If you listen to me, I have said one. I have insist on this point because I know the way I write. Okay, C and K 1 minus 1 over m. Okay. Okay. You okay with this?
Yeah.
Okay. It's a nice remark because I think that you are not the only one in this situation. Okay, but I try to. If we are totally honest, okay, this one looks like this one and not the other. Huh? You just have to count. 1, 2, 3, 4, 1, 2, 3. Okay? Okay? And I repeat that don't be too much hard with me because in general when I correct your copy, okay, I see something that is stranger than what I do. Really. Stranger and stranger. Okay? And I try to understand what you do. Okay? Last exercise for today, and maybe I will start, if I have time, the part concerning continuous random variable, or I will start it in the session. I'm not sure. It's the exercise 12. Okay? It's an exercise concerning geometric distribution. I consider a geometric distribution, and I want you to prove this relation. Okay, so we are going to do the computation, let's say basically. After, I will give you an interpretation of this result here. In other words, okay, what I will answer at the end of this exercise will be the following question. Is it, let's say, interesting to model the lifetime of a car using a geometric distribution? Or the lifetime of a human, or the lifetime of a cat, if you want, okay? With this kind of distribution, the answer will be no, and the argument will be this little relation. But for the moment, okay, just compute this. Okay, so I give you a few minutes in order to try to compute. You know the distribution and the definition of a geometric. You know the definition of the conditional probability. You are able, a priori, to do the computation by yourself. Okay? So try to do the job. Come back to the definition of the geometric. I will remind you. And then we have to compute. So it's the last exercise of the list 4 that we are going to do. So if I am a geometric of parameter p, what is the probability that x is equal to k? What is the probability that x is equal to k for a geometric? P. Yeah. So this one, and be careful, this is true for k belonging to n star. The number of way I have to wait until the first head appear, at least one. So k doesn't start from 0 for the geometric, but it starts from 1 with the definition of my course. Okay? And be careful, because maybe if you change the textbook, you can have an equivalent but little bit different definition. But the one I take here is to be able to interpret it, okay, as flipping a coin several times and wait until the first head appears. If P is the probability to obtain head. That's why I take this definition. In some state books, okay, you have a k instead of a k minus 1, and it starts from 0, not from 1. The problem is that, okay, you don't have the interpretation with putting a question. So try to do by yourself. Okay? You have a conditional probability to compute. And in general, it's something that I have already said to you, is that I have, let's say, something that is simple here, okay? Something that is a little bit more complex. A priori, I start more with this one than with this one. I prefer to simplify than to complexify the things. Okay? Here it doesn't change too much, but sometimes, okay, it may change. Okay, so start from something that appears to be more complicated and try to simplify it. So you have everything on the board. You have the definition of the geometric, and you have to do the composition. So try to do, you take a pen, a paper, and you do, and the way we do maths, it's not looking at the wall, okay? don't remind, the midterm is after the holidays? Yes? Okay. Okay. So I think that maybe I will organize a Zoom or a Skype session if you have some question during the holidays. The Friday, something like this, okay, in order to leave you time in order to work, okay? The Friday, I can give you, okay, 1 or 2 hours. You can enter the room if you want, and I will answer the question. Yeah?
There'll be some sort of like practice, there'll be some sort of practice midterm that we can have.
Yeah, you will have it. Yeah,
Okay.
of course. I will give you the midterm exam of the preceding year just before the holiday in order to train.
Okay.
For 1 hour exam, you will see. In general, it doesn't change that much.
Okay.
Well, I have to change because
Right.
but it will be in the same spirit.
Yeah.
Okay?
And what's the percentage that the midterm exam for 12 marks?
What?
The midterm exam, how much does it count for 12 marks? Is it 30%, 40%?
You have 20% for attendance, and if I remind you have 40 for the midterm and 40 for the final. But let's discuss about this, or maybe a little bit different, but something like this. Maybe it's 30, 60, okay, 30, 40. A priori, the midterm is 1 hour and the final 2, but it's not me that do this convention. Okay? And be careful because a 1 hour exam is I don't like this, but it's not me. Yeah. The midterm will be 1 hour. Very, very short. I don't like this kind of exam, but it's the rule for all the programs. Yeah. But in 1 hour, okay, if you lose a few times at the beginning, that is the end.
But the lesson is also designed for 1 hour, no?
I will design it for 5 or 6 hours in order to give you bad marks. Because it's my, my joy. Every morning I wake up and I say, oh, it will be a wonderful day because
I'm not doing that.
No,
I'm
of
saying that the
course.
exam
It will be a short
happens the
exam.
same.
No, of course it changes a lot. Huh? 1 hour is very short, so it's not possible to have big computations or something like this for sure. No, and I want to ask you this. But you will see, I will give you an example of the exam of the previous year, okay, just before the holidays in order to grade. You will see that they are inside something that we have already done together, little things from the course, and maybe a new exercise, okay, but without big computations. Okay? So I start from the complicated part, okay? Let's say the one that is less simple to write. That is the conditional expectation, the conditional probability. Okay? And this one. So, what can I do? One way to start. It's what I have a conditional probability. I can try to apply the definition of the conditional probability. P of A given B is P of the intersection over P of B. I say nothing, I just use the definition of the conditional probability, nothing more. Okay? So here, for the moment, I use nothing instead of the definition of the conditional probability. Just have a look here. I have this statement, and here I have greater or equal, and here I have strict. Okay? Keep in mind that I am in the discrete case, and typically in the geometric, so my values are 1, 2, 3, and so on. So what is the meaning of being strictly greater than K0? In the case of this particular situation. Yes, so here, since the geometric distribution take values in n star, so only 1, 2, 3, and so on, if I am strictly greater than K0, it means that I am greater or equal to the next value I can take, okay? If I am strictly greater than this one, it means that I am greater or equal to this one. Okay? In order to have, okay, all the terms of the same form, in fact. So I apply what I have said. So it's not true in general, this. It's true when I work with a discrete random variable taking values in capital N or a subset of capital N. You will see that in the case of continuous random variable, we will do exactly the same exercise for the exponential distribution. It will be a little bit different because we don't have such a property in the case where you take a continuum of value. If you take values between 0 and K0 and K0 plus 1, my argument doesn't hold. Okay? So here it's because I am in the discrete case. Okay, so I do the job here. Probability that x greater than K0 plus K intersected with x greater than K0 plus 1 over the probability that x is greater than K0. Okay? My question is it possible to simplify a little this one?
Formal part.
Hmm?
Maybe like the formal part.
This one?
Yeah.
I have to be careful because look at this. K and K0 take values in n. So I just have to be careful because I have one case to consider. Because your friend tell me that this one greater than this one and this one greater than this one means that I am directly greater than this one. I am okay, but except for one particular case, that is the case where K equal to 0. So, what happens if K equal to 0? If I suppose that K equal to 0, that I have here the probability that I am greater than K0 intersected with the probability that I am greater than K0 plus 1, so it's this one that works. And so the ratio is equal to 1. And of course the ratio is equal to 1 because if you plug here in the right part of the equality K equal to 0, you obtain once again 1. Okay? But I have this. And if K is strictly greater than 0, that is K greater than 1, I am agree with your previous argument, that is, if K is greater than 1, to say that I am greater than K0 plus K and greater than K0 plus 1, just mean that I am greater than K0 plus K. Okay? I want to simplify this intersection, but I just have to be careful because in my statement here, I have the case K equal to 0 that I have to take into account, so that's why I have to distinguish between these two cases. Okay, so if I look what I want to prove now, I said that for K equal to 0, here I have 1, And here I have also 1 for k equal to 0 because x is the geometric. So the probability that the geometric is positive is 1 for sure. Because the probability to be greater than 1 is 1. So for k equal to 0, in fact, I have done the job. If I am in the case k greater than 1, this conditional probability may be expressed this way. So I have to prove that this ratio is equal to this expression. And in fact, what do you see? You see that you have 3 times the same kind of term to compute. If I want you to compute this term, you have to compute the probability that x is greater or equal than some 1. For this one, the same. For this one, the same. Okay, so if I compute for this one, then plugging k0 plus k instead of k, or k0 plus 1 instead of k, I will have what I want. Okay? So I repeat, I said that. May I erase this? Okay. I said that if I want to solve my problem here, and to prove that the conditional probability is equal to the right part, the only thing I have to compute is the probability that x is greater than I, or I greater than 1. It's what I have to do. If I am able to compute this one, replacing I by k0 plus k, I will have this term. Replacing I by k0 plus 1, I will have this term. Replacing I by k, I will have this term. Okay? And so I will just have to do the ratio and to compare with this quantity. So for a geometric distribution of parameter p, I have to compute this term. Okay? So what is the probability to be greater or equal to y? It's the probability to be equal to I, or the probability to be equal to I plus 1, I plus 2, and so on. All these events being pairwise divisions. Okay? So I can write this probability as the sum from, let's say, j equal to I to plus infinity of the probability that x is equal to j. It's exactly what I have said. I can be equal to I, or equal to I plus 1, or equal to I plus 2, and so on. Okay? I don't use the classical indexes because I have already in my statement k. That's why I use ij. In order to avoid confusions between the names of the indexes. It should be possible for me to use n and m, but I don't do it. So I have this. So I replace by the definition of a geometric. So I have this sum to compute. If I is equal to 1, I know that the sum is 1. But here I start from an arbitrary I with I greater than 1. So it's exactly as in the previous exercise. I have a sum starting from I. I have nowhere in the course classical sums that sum from other things that 0 or 1. The idea is come back to this case, to come back to classical sums, I know. And to do this, I will change my index. Okay? I change my index in order to make this sum start from 1 here. I is greater than 1. Okay? In the case of the geometric, the sum starts from 1. Okay? So, I want to make the sum start from 1, okay, I have to change my index. So what is the new index I can define here? Something that is equal to 1 when j is equal to I. This one. And I explain why I do this, because with this new index, g prime, I want a sum starting from 1, as we have in the case of the geometric distribution. I repeat why I do this, because from the course, I know this from the definition of a geometric. I know that I have this one from the definition of the geometry, because it's the sum of the probability related to all possible values of a geometry. So if I change my index this way, I will obtain the sum starting from 1, because I have done the job to obtain exactly this. P doesn't change. And I have 1 minus p to the power what? G to the power of 1 minus p. What is the power I have to plug in? Yeah. So j, that is the old index, becomes the new plus I minus 1. Okay, so here j plus 1, plus I, excuse me, minus 1. So if you are not that fluent with kind of index for the moment, you can still use the new name of the index, okay? So you put j here or j prime, it's exactly the same, because the name of the index doesn't matter. In general, we keep the same. Yeah.
Minus 2, no, minus 1.
Yeah, you're right. So because, yes, I have the new and the old. The old is j prime plus I minus 1, and I have forgotten the minus 1 here. Okay, right. So I will write it this way. Thank you. So be careful, you see, be careful when you change the index, because, okay, here I have replaced here, but forgotten the minus 1 here. And if you forgot this one, it will change the value. Okay. And then I take into account what I know. I know that this sum is 1. Okay, because I have here something related from the definition of a geometry. The sum of all these terms is equal to 1. And I see that these terms appear here. I have p and 1 minus p to the power j minus 1. And the sum of this one are 1, and so I obtain at the end 1 minus p to the power I minus 1. Because I have this. These terms have a sum equal to 1. I see that here I have this kind of term. It's p, 1 minus p, j minus 1, and it remains 1 minus p to the power I minus 1. That is here, the sum of the other term being equal to 1. Okay? If you want, I put this one into factor in order to make appear these terms, and I see that the sum is equal to 1. So here, if you want, you have a sum that is equal to 1. I don't write. Okay, so you have computed the probability that the geometric is greater than I for any I greater than 1. You obtain 1 minus p to the power I minus 1. Why not? Okay? But keep in mind what I want to do. I have this to prove. I just have to replace, because you have this general value here for any I that occurs. And so, if I compare what I have from what I want, that is the probability that x is greater than k, for k equal to 0, this is equal to 1. For k greater than 1, I can apply this formula, and I obtain 1 minus p to the power k minus 1. And here, for k equal to 0, I am 1. For k greater than 1, I can continue the computation of this term. I have, for the numerator, 1 minus p to the power k0 plus k minus 1. And below, 1 minus p, k0 plus 1 minus 1. At the end, I obtain simply 1 minus p, k minus 1. And I see that this one coincides with what I have here, using 3 times the little computation I have done here. Okay? And once again, the most important thing to have in mind here is that I have this sum that I know from the definition of a geometric. Let's try to use it in what I want to compute. And you will see that in the case of continuous random variable, we are going to see together. We'll start maybe today, 10 minutes. I don't think so, but we are going to start next session, okay? Then we will do the same with integrals. You will have classical integrals that you are able to compute easily from the course. We are going to come back, if possible, to these known integrals. Okay? It's exactly, we are going to spend, okay, 4 sessions to do this in the continuous case. So for discrete, it's sums that we have to use. The known one, okay, we have 2 mainly. The one dealing with the exponential and the one dealing with the geometry. For the other one, okay, it's finite sum, so it is a little bit simpler. In the case of continuous random variable, it will be integrals for the exponential, the uniform, the Gaussian, okay, and so on. So are you okay with my solution here? So I will do course during the next session, okay, and I will start, so maybe I will do really course, so more than 2 hours. We have the beginning, you will see that the very beginning is the same, okay, and then we have a difference between continuous and discrete random variable, because you see that what characterizes a discrete random variable is the probability that x is equal to a particular number. For continuous random variable, the probability that my random variable take a particular value is 0 every time. So it's something that is drastically different. Okay, so we are going to use other tools in order to define such cases. Okay? Questions?